Matter is constantly rearranging. In a physical change, such as ice melting into liquid water, the state of the substance shifts, but the underlying identity remains constant. When that underlying identity changes, a chemical reaction has occurred. This is the physical process of breaking existing atomic bonds to forge entirely new ones. Because we cannot observe individual atoms, we rely on macroscopic indicators to signal this shift. We look for a sudden change in physical state, a shift in color, or a spontaneous change in temperature. Another indicator is the rapid evolution of a gas. For example, when magnesium is exposed to heat and oxygen, it reacts by bursting into a blinding white flame, leaving behind a brittle white powder. Documenting these instantaneous events using standard sentence structures, like magnesium ribbon burnt in oxygen converts to magnesium oxide, is inefficient and imprecise. To accurately track the chemistry, we must move past macroscopic descriptions and adopt a specialized shorthand mathematical model. The first step is the word equation. In our magnesium example, we write magnesium plus oxygen yields magnesium oxide. This establishes the basic geography of chemical notation. The reactants occupy the left side, while the products occupy the right, separated by an arrow showing the direction of change. We then translate those words into chemical symbols. Magnesium becomes Mg, oxygen gas becomes O2, and magnesium oxide becomes MgO. This unadjusted formula, Mg plus O2 yields MgO, is known as a skeletal chemical equation. This skeletal model contains a critical flaw. While we have 2 oxygen atoms on the reactant side, we only have 1 on the product side. This imbalance violates the law of conservation of mass. In a closed system, atoms cannot be created or destroyed. Failing to account for every atom, the skeletal equation is an incomplete model. It lists ingredients, but disobeys the physical laws governing mass. To resolve this, we will apply a more rigorous method to a complex reaction, iron reacting with water to form iron oxide and hydrogen gas. This graphic shows our unbalanced equation alongside a ledger tracking our atomic inventory. Looking at the iron row, we have 1 atom on the left but 3 on the right. The oxygen row shows a similar deficit, 1 on the left, 4 on the right. The ledger proves the mathematical model is out of sync with reality. We must correct the math without altering the chemical identity of the substances involved. We begin the hit-and-trial method by drawing impenetrable boxes around each formula. We prioritize the compound containing the maximum atoms, Fe3O4. Here, we target the element with the largest imbalance. Oxygen has 4 atoms right, but only 1 left. To fix this, we apply whole number multipliers, called coefficients. These must be placed strictly outside the formula boxes. We balance oxygen by placing a coefficient of 4 in front of the water box on the left. We cannot simply change the subscript to H2O4. Altering a subscript fundamentally changes the chemical's identity, transforming stable water into a different, highly unstable molecule. The ledger reveals a side effect. We now have 8 hydrogen atoms on the left. We correct this by placing a 4 before the right side hydrogen box. Finally, placing a 3 before the left iron box completely balances the ledger for all elements. By manipulating these external coefficients, we have forced our theoretical paper model to align with the physical requirements of mass conservation. While mathematically balanced, the equation still lacks a description of physical state. We complete the model using 4 symbols, S for solid, L for liquid, G for gas, and AQ for aqueous solutions. This finalized equation reveals a specific detail about the reactants. Note the G attached to the H2O. This symbol indicates that the iron reacted specifically with steam rather than liquid water. The addition of precise quantities and physical states creates a high-fidelity model of the reaction. With a rigorous modeling system in place, we can categorize how atomic bonds structurally rearrange. The first archetype is the combination reaction. The structural rule for combination is the merging of two or more reactants into a single unified product. This is the reaction used in whitewashing. Solid calcium oxide and liquid water merge into a single product, aqueous calcium hydroxide. This structural merging releases significant heat into the surroundings. We define any reaction that releases heat alongside products as an exothermic reaction. Combination reactions are characterized by structural unification, a process that frequently releases energy to the environment. The inverse of this process is the decomposition reaction. Structurally, a single reactant fractures into multiple simpler products. Severing existing chemical bonds is never free. It always requires a dedicated input of energy. We can force this split using electrolytic energy. Running an electric current through water physically separates the molecules into pure hydrogen and oxygen gases. A second pathway is photolytic energy, or light. White silver chloride powder will decompose into gray silver metal and chlorine gas simply by being exposed to the sun. The final pathway used to force decomposition is thermal energy, or heat, which is a standard requirement in industrial manufacturing. While decomposition reactions diverge structurally, they share a universal thermodynamic trait. They exact a strict energetic toll that must be paid in electricity, light, or heat. Whether atoms are merging into complex structures or fracturing apart, their interactions are strictly governed by the physical laws of mass and energy. This system ensures that every atom is accounted for, maintaining the link between chemical theory and physical law. The resulting ledger provides a precise, balanced record of how matter is redistributed across these chemical categories.